environment. So I'm going to be discussing here about the different aspects in the next 3 hours of implementation of QKD protocols. So it's going to be mostly on the board and a little bit of support of a few pictures on the slides. And towards the end, I have a few slides that I can show you with a little bit more global information. So we're going to go through different topics. I will need as well your feedback to tell me if you know some stuff, if some things, it's not always easy. Sometimes some of you may know some things, but so hopefully it will be interesting for everyone. You have seen in the previous days in detail the security proofs for quantum key distribution protocols, discrete variable, essentially. So what we're going to do today, I'm going to go through a few aspects that come into play when one wants to implement in practice these protocols. It's going to be mostly like a theoretical analysis in the sense that I'm going to be writing down a few equations to explain what I want to say, but it's going to be a security analysis, for example, in BB84, when one takes into account the fact that you have some deviations between the assumptions that you have in the security proof and what happens in real life, which is something that was not known immediately in the field initially when the first QKD protocol, BB84 in particular, was invented. It was not immediately seen that using realistic components in real life will actually open security loopholes, right? And so this has to be taken into account either by considering them in the security proof or by doing countermeasures. We're going to see all of this. With a specific focus, quite a big part of the lecture will go into the decoy state analysis, but not only, we're going to also see different types of encoding of the information in these protocols, and also a little bit some information about components. For those of you, especially who are not experimentalists, those of you who are experimentalists, you're seeing them in your everyday life, or you will see them when you do experiments. And then some more information on side channel attacks and testments. Good. Okay. So maybe we can start with a little bit of a generic view. So you need to tell me if you see. I'll try. I saw that Renato had written huge letters in his lecture. So I'll try to do the same. I have a hard time. Usually I write a bit small. So I'll try to write big. So maybe we can look how a system, and we can go into the details, how a QKD, an implementation of BB84 or any, for that matter, QKD protocol will look like. First of all, we will have the generator of the qubits, right? I should clarify here that you may of course know that there are QDIT as well, right? So there are even quite a few works in quantum information now that work with higher dimensional quantum systems, not infinite dimensional. I'm not talking about CV keys here. I'm talking really about QDITs, okay? D-dimensional things. I'm not going to be talking about this here, okay? So there has been quite a bit of work on QDIT-based QKD. So this is not something I'm going to touch in this lecture. There is a lot of work, so you can ask me if you want references. Maybe some of you work on it as well. So there are specific things that one has to think about when they're talking about the qubits. So it's going to be qubit, and then we have the encoding, of course. The encoding. Then we have the quantum channel. So this is a generic representation of the decoding. And detection. And so what we're going to do essentially in this thing, we're going to go a little bit in each one, in a little bit of a convoluted way, in each one of these building blocks of a generic quantum system, and see what assumptions are included in such a representation, and what this means for the security. So as I was telling you, we're going to spend quite a bit of time on the fact on what does it mean to have a qubit, how does this relate to what you saw in the security proof. The ideal security proof tells you that Ali sends to Bob a qubit, right? A single qubit. What does this mean in practice? What does this imply when this is not quite the case in practice? We're going to be talking a little bit of characteristics of the quantum channel, how you can encode and decode information, and the detection techniques, what are typically used, and how does this affect the security? The fact that, again, in the security proof you saw that you have Bob who, in a prepare and measure QKD protocol, measures the qubits perfectly, you know, in one of the two bases. And so how does this work in practice? So let's go and look a little bit at the encoding. Okay? The encoding, what do we usually do in this? So this is the vision of prepare and measure using variable QKD. Okay, this is what I'm going to be focusing in mostly here. So encoding will happen in the two orthogonal modes of the electromagnetic field. Okay, so this is what we call dual-rail encoding, usually, in this language. So we need to define the two states of the computational basis Z. So something that we're going to be using, and a notation that I'm going to be using is this, where you have the 0, that is going to be your 1 photon in the A mode, and 0 photons in the B mode, or the 1, okay, this is, is going to be, okay, so these are the states of the qubit states. So a very natural two-dimensional space for QKD is, of course, which one? If you had to pick one degree of freedom that the people use to encode quantum information for QKD, which one would you pick?
Time beam.
What?
Time beam.
Time beam is the first one that you would pick.
Polarization.
Polarization. Very good. This is exactly what I'm going to be talking. We're talking about polarization and about time beams. Okay, so it was a but so a very, very natural, so two-dimensional space is polarization. So for example, in this we would have this computational basis would be horizontal and vertical. Okay, usually this is what we write. So just for those of you who are not physicists, although from what I understand most of you are physicists, polarization, remember what it is, okay? It's a property of the transfer electromagnetic field that shows that there is a privileged direction of the wave, okay? And so this is the privileged direction of the wave, is called polarization. While the phase, which is another property that is very, very much used in practical implementations of QKD, is the specific position on the waveform, and it takes a periodic values. Why polarization is a good degree of freedom to perform quantum information, in QKD in particular, it's because it's quite easy to manipulate, okay? So we have, for example, optical components that are called wave plates, okay? Don't know if this rings a bell to some of you. So we have wave plates, which are passive optical components, okay? Passive optical components is that you don't need to apply a field, an electric field or something, to the component. It means that you just insert it into your system, okay? Passive optical components are easy to use, okay? We like them, they're easy to use. They are, you essentially put light into them, and because of the material, it kind of transforms the state of your waveform. So, for example, a very well-known component is the half-wave plate, okay, which is an optical component that changes, that applies a pi phase shift between the two modes of the electromagnetic field, and therefore, for example, you can understand it is something that moves from one linear polarization to another. So it's an optical component that we use like a lot in all these implementations of polarization encoded QKD. Other passive optical components, so maybe I should write it here. So half-wave plate. This is how we talk about it. And then other optical components that we use really a lot in practical implementations of QKD are the beam splitter. Okay, the very easy. Okay, So this is a 50-50 beam splitter, so we'll be using something that is called, I'm going to be showing to you a little bit more in detail this particular optical component. I'm going to even analyze it with creation and distraction operators, etc., because it's a fundamental building block of implementations of QKD and other quantum cryptographic protocols, okay? But I'm just giving it to here, essentially. So this is a device, okay? This is a device. If it's an equilibrated 50-50 beam splitter, it essentially divides the light, okay, into two directions. And this can happen for polarization as well. Another component that is well known and it's extremely useful in polarization and coding implementations is the polarization beam splitter, okay? That you can look like this. And this also we're going to see it in more detail later. So the polarization beam splitter, it has this particular property that if the light is there in a superposition of horizontal and vertical light, okay, it will let through the horizontal component and it will deflect the vertical component. Okay, so this is an extremely useful and important component of QKD and of general, again, polarization and coded quantum communication protocols. At the very end of the lecture, we're going to see how these two devices can be used to perform a so-called Bell state measurement, okay, Bell state measurement for polarization encoded for one type of QKD protocol that is called measurement device independent. But I shouldn't be going too much ahead of my time. But these are components that are extremely useful for polarization encoded quantum information protocols. Now, on top of this passive optical component, okay, there is other stuff. I'm not going to be talking about all of them. There is variable attenuators, okay. For those of you who do so, we know how to attenuate light optically, okay. We can do these type of things. We can, in general, manipulate, okay, these properties of light optically, especially when it comes to polarization. Another type of components that are very useful are the active optical components like modulators, okay? So modulators are extremely useful components that we use in both discrete variable and continuous variable QKD. So maybe some of you have seen them. So what do modulators use? Essentially, they are elements, okay? There is a non-linear optical material that is used. For example, a very common one that is used in devices that we use in QKD implementations is the material that is called lithium niobate, okay? For very fast optical modulators. So what's happening is these materials feature what is called the electro-optic effect. So for example, you can use this non-linear material here, okay? Lithium niobate. You can apply electrical effect to it, and what can be shown is that then when you do this, the light that comes into it, okay, what happens is that you change the index of refraction of the material that is inside, that the modulator is made of. And this index of refraction means that the speed of the light inside this material changes, okay? And because the phase that is accumulated by the signal that comes through this material depends, is proportional, is exactly proportional to the time that it takes to transverse this material. It means that you can essentially, by changing the electric effect that is applied on this material, you change your phase. Okay, so this, for example, the simple device that you see here is what is called the phase modulator. Okay, by putting it like this, by changing, by driving, and this is why this is an active optical component, because you have to apply an electric effect, okay, an electric signal to it, the voltage, and so when you apply this effect to it, this changes the properties of the non-linear optical material, the refractive index, changes the speed of the light, and so the phase, okay. And so this is called the phase modulator. This is a ubiquitous component in QKD protocols implementations and more globally. And then when you want to, so this changes the phase of your incoming signal. If you want now, if you want now to change the intensity, all you have to do is to create a so-called Mach-Zehnder interferometer. modulator inside the arm of an interferometer. Okay, this is a beam splitter and another beam splitter. You apply your phase here. The forward modulator here is you apply this effect. And what does it do? It essentially splits the intensity that comes into the Mach-Zehnder interferometer. Okay, one part of it goes through the phase modulation, one part of it does not go through it. It changes the phase between the two arms, and so you create a destructive or constructive interference at the output of this device. And essentially, this allows you to modulate the intensity of your signal. So this is an amplitude modulator. Modulator. Okay, phase modulator, I repeat, non-linear optical material, electro-optic effect, and so you can change the phase of your signal. Amplitude modulator, you just put your phase modulator into a Mach-Zehnder interferometer, and so you, like this, you can vary the intensity of your signal depending on the effect, on what you apply on the phase modulator. So these are very, again, crucial components of QKD systems. So these are active components, while these are passive components. And so, this allows you to essentially modulate your signal, the signal that comes, and code the information that you want to encode of your signal. We're going to see exact cases of how this is worked, of how this works. And now the last part that I'm not going to be giving all the details now, because we're going to be talking about them a little bit in more detail because of their importance later, are the single photon detectors. Okay, the single photon detectors here are devices that are, again, ubiquitous, of course, involved in every single implementation of a discrete variable QKD system. So the most, maybe I can give you one general comment here, that the most widely used single photon detector in implementation is the so-called threshold detectors. Threshold detectors, okay? What does the name mean? Threshold detectors means that single photon detectors, it means that they can tell you if you have one photon and above. Okay, they cannot discriminate between the number of photons that are hitting the detector. So if you want mathematically, you can write them with a POVM, with a positive operative value measure. I'm assuming here that everybody knows, okay, POVMs. So the POVM here can be written as pi0, where the pi0 is simply the projector onto the vacuum state. The vacuum state, I'll be mentioning it as omega, so that we cannot do not confuse it with the zero of the other qubit notation. Okay, and so a threshold detection gives you exactly that. It's a projector essentially on the vacuum state, and everything else, the second element of the POVM, is everything above. This is essentially, I'm going to be only talking about threshold single photon detectors in this course, but keep in mind that there is more and more work on photon number resolving. They are called PNR, photon number resolving detectors. So these are detectors that can actually tell the difference if they are hit by pulses that have more than 1, 2, 3, 4, 5 photons. Okay, it's really hard experimentally, not easy. And there is always, in the current devices, there is always some error. Okay, there is some overlapping, let's say, signals between whether you have 2 or 3. But still, sometimes if you pick the correct peak, it allows you to perform photon number resolution measurements, and this is kind of important. Not really for QKD. It's not really hasn't. Been proven that is particularly useful for protocols for QKD, but for other protocols it can be useful. this photon number resolution. For QKD, threshold detectors are okay, but of course we're going to discuss what this means in practice. And so what are the characteristics? Maybe I can tell you that as well. The characteristics of single photon detectors that are important are the quantum efficiency, okay, the quantum efficiency of the detectors, which we typically write as eta, okay. Quantum efficiency tells you what is the probability that a photon that has hit the detector will actually provoke a click, okay, a detection event. We're going to see a little bit the physics behind single photon detectors later, so you will see what this means. And then the dark count rate, okay, the dark count D, which means what are the false positive events when we have a count in our detector, despite the fact that there has not been an actual photon that hit or a signal photon that hit the device. This makes me think that I forgot to tell you also the important characteristics of the modulators. So when you build a modulator like this, what are important characteristics? The insertion loss, of course, as we will see later, all losses in a QKD implementation are crucial. So you want to minimize your losses everywhere. You know, QKD is protocols like all quantum information protocols, in fact, but especially QKD because of all the security constraints and because of the fact that the channel is given to the eavesdropper, right? All losses are important, and so you need to minimize the insertion loss. Other characteristic that is super important is the speed or the bandwidth, okay, of the modulator that tells you. That tells you up to which frequency of the incoming light you can have the effect that you are looking for. Okay? You can actually modulate your signal. How fast can it go, your wave, before it's not possible anymore to modulate your signal. And extinction ratio, when you want to create, for example, different states, is like how well in intensity modulator, for example, in amplitude modulator, the extinction ratio will tell you what is the difference between the top of what you can modulate and the minimum. Okay, you would want to have a very big gap between the two to be able to create states that go the maximum possible and the most closer to zero. Okay, to create a good depth in your signal. These are the type of characteristics that are important for modulators. Good. Questions on this part of what I've said up till now? Good. Okay. So then we can draw based on this information that we have now a possible experimental setup for BB84. This guy will show you how it could look. An experimental implementation of a BB84 could look like. You can have a combination, for example, of passive and active components, or you can have it fully passive, for example. You can make different choices, but here is an example of how this could look like. Here, for example, I've shown you that you can use, I haven't touched yet the issue of single, of how you generate the qubits. You can say that you have a single photon source. You can use an electro-optic modulator. Now that you saw what this is, you can use electro-optic modulator also to modulate the polarization of signals. So here, for example, you can use it to generate the four BB84 states, okay? And you would have to do this, of course, completely randomly, according to the QKD security proof. Then the quantum channel, and this is an example of how a measurement device, a decoding, so this would be polarization and coding, okay? And the decoding setup would be this one before the detectors. Here it's represented by a 50-50 beam splitter, okay, which is what you see here, and followed, okay, so this would split the signal in two, followed by two measurement stations. One measurement station is a simple polarization beam splitter with two single photon detectors behind, okay? And so this performs the projective measurement in the Z basis. Do you see why? You see why this is sufficient to perform a measurement in the Z basis. What does this do? It takes the qubit, okay? What did we just say? It is in some polarization state. And what this tells you is that it's going, the H component is going to go through. This is what we said about the PBS here. The horizontal component is going to be going through and be detected here, okay? The vertical component is going to be deflected, okay, and we detect it here. So it's actually, this is a measurement on the HV basis, okay, which is the computational basis for polarization encoded QKD. And then if you want to do it for the X basis, okay, for the plus or minus basis, you need to know, you know now what this is. You need to turn your signal by a half-wave plate, okay? You move it, you move your polarization, and then you project it as well in the same way with a polarization beam splitter and two single photon detectors. This is essentially a measurement, okay, an experimental measurement on the X basis, on the plus or minus basis. If this is not clear, tell me. It's like very important, right? This shows you how easy is, essentially. That's why we like this type of encoding, because it's actually from an experimental point of view, it's very easy to perform this measurement. These are all components that are very easy to find, and you just switch, okay? You switch your state and you project essentially your state in the other polarization basis. So see, this is one example of an implementation of EB84. As I was saying before, you can also do everything passively, okay? And you can even use, like it was done, maybe Thomas will show that tomorrow in the space, maybe or maybe not. For example, in the Mischius, in the Chinese satellite experiment, the qubit, okay, generator were 4 separate lasers, okay, 4 separate lasers, and each one was preparing one of the 4 polarization states, and then they were combined, and this was forming alleys, okay. So that's why I'm telling you, there's not a single way of doing experiments, but the components are more or less what you see here. Okay, so this is an example of how you can do BB84. So now it's important, you mentioned time being, so I wanted to mention one more encoding scheme. It's important to remember that there is not a single way. I was focusing a lot, I focused on polarization because, I mean, it's very extensively used, it's easy to understand, very easy to manipulate and everything, but time being encoding is also very important. So maybe this allows me to go back a little bit to the notion, to show you a little bit of a different example of how this can work, okay, of how this can work. And remember a little bit the modes that we were just discussing. So remember here, because this is something that we use a lot in quantum information more globally, and sometimes even physicists are not sure what we mean by a mode when we talk about a mode of the electromagnetic field or a mode in general. We talk all the time about modes. So remember here, there is even whole books and articles about what a mode is, okay? So it's a normalized solution of Maxwell equations, okay? Maxwell equation in vacuum. So basically you can consider the mode as a set of properties, okay, of the field that are conserved during propagation inside the vacuum, okay? This is more or less a global definition of the mode. And you can have you can have spatial mode. This is something that we're going to be seeing. You can have time frequency mode, or you can have polarization, which is what we just saw. Okay. So spatial mode, we're going to see it a little bit. It's related, of course, to the direction of propagation, but also to the spatial shape of your mode. Time frequency is extremely important. It defines essentially the frequency of your waveform, or completely equivalent to the center of the time center, okay? The central position of the wave packet, and then polarization that we just saw. So of course, quantum physics tells us that each mode is quantized, okay? The field is and the single photon is essentially the excitation, okay, the single excitation of a particular mode of the electromagnetic field. Okay, single photon is a single excitation of the electromagnetic field of a particular mode of the electromagnetic field. And so with each one of these modes, we can associate a distraction and creation operator, okay? And this is how we essentially propagate, how we see in practice how the state changes through an optical setup like the one that you've shown, okay? Often in quantum optics and in quantum photometry, this is what we do. We see what each one of these elements does to the operators in the Heisenberg picture. Okay, we work with operators rather than with states, and then like this you can see exactly where your what is the probability that your photon will go in which direction. This is completely how we work. Like for example, if I can show you the beam splitter that we saw before, we can look at it as something that has two input modes. How do I put it here? Okay, so A0 is the one input mode, A1 is the other input mode. Sorry, it's a little bit small. A2 is the output mode, and A3, okay, the A2 and A3 are the two output modes, and you can show this description in this operator picture can become extremely easy. You can see, for example, that A2, again in the Heisenberg picture, the creation operator for a 50-50 beam splitter is going to be A0 plus A1, so this is the creation, sorry, I don't do it. And then A3. There is various ways of describing beam splitters. This is one of them. So you can put, for example, some phase factor in one of the two directions. Okay. So by doing this, essentially, you propagate, and we're going to see later how you can do the same thing with a polarization beam splitter, and so you can somehow see what happens to your waveform when it goes through these optical elements. Okay, so this was a little bit of a deviation around modes so that you can see a little bit how it works, and this allows us to give now the scheme of BB84 with a time bin encoding. So in the time bin encoding of BB84, what you are going to use is that we are going to use two pulses that have a width of the delta t, while they are separated by the delta t that has to be bigger than delta t, okay, so that they are well separated into time, okay, and you are going to use this time as a reference, so you need to have these two orthogonal modes that are essentially two non-orthogonal pulses that are temporally at different times, okay, and they go through the same spatial mode, the same channel. Okay, this is what is important here. Now that we have seen the modes, the time, etc., so this is what essentially defines your initial input state. Okay. Tau 1, and this is Tau 1. This is your initial state, and what does a time bin based BB84 system looks like? What you want to do now is that we want to create a coherent superposition of these states. This is something that is very easy to do in polarization. Create coherent superposition between, because you want to have, your BB84 bases, your two BB84 bases. Here, this is something that is done very easily by these electro-optic modulators in polarization. If you want to do this coherent superposition for time bins, you need to create an interferometer. Okay, so you need to input your initial state like this inside an interferometer, an unbalanced interferometer. So this is the short path. Okay, and this is going to be the long path. Okay, that we're going to be calling L. Here we're going to put a phase element because it's going to be important. This is Alice, so she's going to be able to apply a phase inside her system. So this takes the input time bin qubit, okay? And depending on which path the two paths take, it creates this superposition between the short and the long path, and between the first and the second time bin. Okay. So then this goes through the quantum channel, then they go through both, who has an identical unbalanced interferometer. Again, so normally this should be completely balanced, S and L. Okay, short and L. This is the quantum channel. So this is the time being decoder. Bob applies his phase here, and this is very important. Essentially, what happens, you can see it immediately. So depending on where the pulses go, you will have the short peak. Okay, you will have an interference between the short and long here, and the long and short here. Okay, that are essentially going to go in the same, they are going to arrive at the same time at the beam splitter, and you are going to get the pulse that goes through the long path. So you expect in your detection pattern something that looks like that, a peak, whoop, okay, something like this. This corresponds to the short, long, and this to the interference between the short, long, and long, short. Okay, this is how it works, and this is the ones that you are going to use for the creation of your secret key, and the clicks in here, which interference you are going to have, destructive or the constructive, is going to depend on the difference between the two phases that are applied by Alice and Bob. Okay, depending on these phases, you know that your count is going to fall in this central peak or outside, and this is what you are going to use for the creation of your secret key. And you can show that the phases that are going to use for the Z basis are typically 0 pi, okay, and for the creation, and I think it's like Y basis for this, it's minus pi over 2 and pi over 2. Okay, these are the two phases, the two families of phases, the pairs of phases that you need to use for the encoding, the time being encoding of BB84 in this setup. So this is an encoding time being BB84 that opened the way at some point several years ago to nice demonstrations, because if you can somehow find a way experimentally to make these interferometers stable, compact, okay, stable, compact, and identical, though, and this is the difficulty, okay, depends really a lot on how close these interferometers are. It's extremely critical, because otherwise you will not get, you see immediately here that you will not get the right interference if they are not well balanced. And also, so this time encoding gave rise to the very first as well commercial setup of QKD, where before, because this was very difficult to do, what they did, they folded it. Okay, so basically what happened, and I have a picture here of the very first system that was built back then by Diamanti, where essentially what they did is they put back then in Geneva, Bob was creating the signals. This goes with the circulating. You see here the first, the interferometer, okay, the interferometer, and then Bob essentially has to do both the first and the second interferometer, okay. So the kind of all that Alice has to do, so the qubits need to go there. All that Alice has to do, they get deflected. Alice has to apply her phase as we said, and then they go back. And they get detected also by Bob, thanks to a circulator that is used there. So the detection and the laser and the creation of the qubit are all handled by Bob. And this is a sort of folded BB84, which was called the plug-and-play system, gave rise to a very stable, essentially system. Became a very stable system that could be launched. In field test, etc. So it essentially moved the problem of creating this identical interferometer by using the same for both Alice and Bob. Of course, there is one can discuss about the security issues of such a folded system, because Bob has both the detectors and the laser, etc. So this is open. So this has kind of, and the technology has advanced since then. So this has kind of not used anymore. It's not used anymore. Now we have unfolded time beam. I think Thomas will tell you more about this. We have some very beautiful setup like this in Canada. So this is something that is very much developed, and it really helps to create a nice system. Good. So now, essentially, this concludes what I wanted to say on encoding. Yeah?
So your encoding is basically based on the phase difference in this case?
Yeah. Yeah, essentially, you use the time bin, but where you encode the information in this particular case is here, right? Depending, again, the arrival time of your qubit depends on the phase difference between this system. You can see that if it's, I can't remember now what it works, how it works exactly. When it's 0, they will fall inside. When it's pi, they will fall outside. So depending on this, the detection pattern depends on the phase difference.
So is this, how is this different from the phase encoding?
It is essentially a phase encoded system.
Okay.
That use time bin qubits.
I see. So it's basically both the same thing. Okay.
In this particular case. Yeah.
There is no upper bound in the delta T?
There's no, sorry?
Upper bound or any requirement? I mean,
In
can be as greater as we want, or I mean,
delta T, sorry, yes. So delta T, how far they have to be? That's what you mean? Well, it definitely has to be bigger. They need to be separated, okay? Yeah. They need to be separated. Upper bound, this determines how big is the interferometer has to be, right? If they are too far, this determines essentially directly linked to the length of your interferometer, okay? So if it's too big, you will have to have a very big interferometer, and this is always bad. It's like for stability and for to create.
The length of the interferometer.
Yeah. This is essentially what puts, from experimental point of view, the upper bound. Yeah. Okay. Good. So this concludes the encoding things that I wanted to tell you, and now I'm going to move to the qubit. Okay, to the qubit assumption. This qubit assumption that we that has created lots of here. Maybe I'm going to leave it here. So how well justified is the assumption here that we have a perfect single qubit? You know, I saw you in the picture here that we have the single photon source. You know, perfect single qubit. So single photon sources do exist. I couldn't help here giving you like my life as a very young PhD student was this experiment. When I joined Stanford, I did my PhD at Stanford in the US several years ago. and so the experiment that the older PhD student I was working with at that time was in exactly this, a QKD with a quantum dot single photon source. Okay, back then it was a quantum dot single photon source, and his work, he was just literally finishing his work when I arrived, and he had done this dice where he would show with one time pad with keys generated by this quantum dot setup. This is the campus. Okay, this is the Stanford campus, the Memorial Church is called, and so with Alice and Bob Ski, he had created this picture. And back then, you know, in this work, in this quantum dot single photon source work, he had shown this graph where you can see, and this is, I'm going to spend essentially the next chunk of the course to explain what this graph means essentially, okay? Why? So what you see here is that with a laser, which is the blue curve, you get a disadvantage, you get a different behavior, okay? Different behavior of your secret key rate as a function of the loss than what you get with a single photon source. You see here that you get the quantum dot allows you, it has a different scaling. You see that, right, already from this graph, that you get a different scaling between when you use a laser to create your single qubit and when you use a single photon source, a quantum dot in that particular case, to create your single qubit. No, since then, things have evolved really a lot, okay? So that was before the creation, just before the discovery of the so-called decoy state protocols, which we are also going to spend some time, okay, to explain, which kind of solved this problem that creates this difference in scaling that we're going to discuss now, okay? This unfavorable scaling when you have a laser with respect to when you have a perfect and a single photon source. So it solved decoy state protocol, solved this problem without having to have single photon sources, okay? And so since then, experiments like this have gone a little bit silent, okay? So single photon sources have been used for many things, but not necessarily for QKD. But now a few years ago, there are more groups that are creating better single photon sources, even better and better, like and more practical. I'm thinking in particular, but I may be forgetting. So Tobias Heindel in Berlin. There is Rinaldo Trotta in Rome, that have done more experiments with single photon sources for QKD. So it's coming back. So it still needs to be proven that it's worth it. For me, there's still decoy state protocols that I'm going to discuss. They're so mature now that it's difficult to justify using a complex device like a single photon source for QKD. But there is an open question there. It could be useful in some cases and for some other quantum communication and cryptographic protocols. Okay, so this is a personal view. It's not a general. It's an open question. Okay, so this was a historical little point just to show you long time ago what was happening. So going back now to this qubit assumption. So why is there a different scaling? Why is it the problem to not use ideal single qubits in real life? So what's happening, as we said, using a perfect qubit. What is a perfect single qubit? It's that you want to have deterministically in every pulse a single photon. Okay, so this is deterministically, not probabilistically, to have every time that you send, Alice should send to Bob a single photon in a pulse. This is what you would like ideally to have. So this is very difficult to do, okay? And so what have we doing for ages? We have been using weak coherent states, okay? Or attenuated laser pulses, if you want. So this is often this is called weak coherent states, okay? This is the assumption that we use. And so this introduces a critical new quantity in the security analysis that is essentially the average photon number per pulse, okay? So in the next, I don't know how much time, I'll be talking a lot for the average photon number per pulse, because obviously if you have a perfect single photon pulse, you don't have this quantity, right? It's always one. Again, you don't have to worry about that. But when you have these weak coherent states, a quantity that is super important is this one, that we typically write with a Greek letter mu. So let's go through a little bit from the beginning. So what does weak coherent state mean? We're going to be taking the output of a laser. Okay, the output of a laser is a coherent state. This is what we're going to be using because it's a lot easier to use a laser because it's an equipment that we have in our lab, and it creates this coherent state that we're going to be writing here. Many of you will have seen that already. Okay, so this is an expression, the mathematical expression of a coherent state. Careful here, for that part, for the whole part, this whole part of the course, I'll be changing notation. Now, this one is Fock state. Okay, so this notation now is a Fock state, is the number of photons in a single mode of the electromagnetic field. It's not anymore what I was writing before. It was the 0-1, the dual rail encoding. We're using the two modes of the electromagnetic field. This you have to understand now as a Fock state. Okay, so the number of photons in a pulse. Sorry for this juggling between the different notations. And so now, an extremely important point that is often overlooked, and we're going to talk about this a little bit more in the experiment, is that you don't want to have just a sequence of coherent states. You want to have you want to have an incoherent mixture of photon number states, okay? And to do this, you want to have an incoherent mixture, I repeat, of photon number states. You do not want to have just a series of coherent states because this opens a side channel attack, okay? Which we are going to discuss later. So what you want to do is what is called phase randomization. Okay, this is very important in experiments. And often overlooked, often we say, oh yes, we could do phase randomization and we should, but we don't always do it in experiments, okay? Phase randomization means that if you write, for example, your the density matrix of your coherent state like this, then a phase randomized state is going to be looking like this. It's going to essentially the output of all different phases. Okay, so it's the average over all possible phases, and you are with a few lines of algebra that I'm not going to do here, okay? That I'm not going to do here, but I have it if somebody does not see how to do it. You end up something that looks like this. Probability. Okay, which is essentially using this expression of the coherent state, where where this is the expression of the Poisson distribution of the photons of the coherent state with an average photon number pulse, mu equal to alpha squared. Okay, so this is I repeat here, so you have a phase randomized state. That is written, phase randomized state, which is the average over all possible phases of the coherent state, okay, which comes out of the laser. And this, with a little bit of algebra when using the expression of the coherent state, can be written in this expression. So this is exactly what we said, a mixture of all Fock states, where this probability is the Poisson distribution. The Poisson distribution, that is the distribution of photons coming out of a laser, okay, of a coherent state coming out of a laser, where mu is the average photon number per pulse. Okay, so when you get the output of a laser is a coherent state, it follows a Poisson distribution, and this and by phase randomizing the whole thing, you get this state that is an incoherent mixture of all the possible Fock states. So this is the actual state that comes out of your laser when you do this. And so maybe we can even expand it a little bit here. We can even expand it a little bit. This expression, the same expression, we can expand it a little bit and write it like this, probability, so that you can see the importance of the different terms. Essentially, I've done here, I've removed the zero component, the n equals 0 component, and the n equal 1 component, okay? Because this we are going to be overall very, very important, and the one that is actually going to be used that is actually used in all these weak coherent state implementations of QKD is this one, okay? Is the single photon, single photon component. This is the one that is interesting for us, and this is that essentially one that simulates, in a sense, a single qubit. Okay, it's the part of my state, of this phase randomized coherent state, that actually should be, if we had a perfect single qubit implementation of a BB84, this is the component that we would have. Okay, this is the one that is used for the qubit encoding. So now the fact that we have this multi-photon, okay, there is the vacuum, sure, there is the zero photon states, they're a little bit of a problem, but not that much. They break, a little bit the efficiency, you lose part of the signal, but from a security point of view, they are not a problem. The ones that are a problem are these ones, okay, the multi-photon states. They create an inherent security problem in BB84 implementations. Why? Because they allow if to do the so-called photon number splitting attack, okay, that I have schematically shown here. Essentially, what this photon number splitting, sorry, this shock is like getting into my lungs. So this photon number splitting attack can be understood as an attack that looks like this. So you have some cases, as you see, with some probability that is given from the probability here, from this Poisson distribution. You can easily calculate for a certain average photon number per pulse what is the probability of having more than n photons, 2 or more, right? With some probability, you are going to have multi-photon pulses. And in that case, what can Eve do? What Eve can do, this is the attack that she can do. She can perform a non-destructive photon number measurement, okay? Non-destructive photon number measurement. so she can pick the pulses that have more than one photon, okay? The multi-photon pulses, extract one of the photons out of the pulse, keep it in a quantum memory, okay? Wait until Bob performs his measurement, as in usual BB84 implementations. He will announce then, as usual, the basis on which he has performed the measurement. And so Eve at that point can perform a delayed measurement on her stored photon that is in exactly the same state as the photon that Bob received. Okay. So if this attack happens optimally, and we're going to discuss about what optimal means in this case, one can show that Eve can get perfect information, full information on the secret key without creating any disturbance in the communication between Alice and Bob. Okay, so she can go completely undetected under specific circumstances with this photon number splitting attack. Is it clear? Did you see how this attack works? Yeah.
How is the photon number measurement done?
Yeah. So this is a very good question. At this point, from a theoretical point of view, we don't care. It's an allowed operation, in quantum mechanics. We know it's possible. So the mere fact that it's possible, it's enough to define your attack. And now, in real life, performing a quantum non-demolition, because you need to leave your state, you don't want to destroy it, measurement is not easy. There has been some experiments in particular, the ones that I know of, are the ones by Serge Ross at ENS, where you move the state of your photon in some stable system, in some atomic system, it's cavity QKD in particular, in their particular case. So you use cavity quantum electrodynamics, you put where the photon number information translates into excitation of your cavity QKD system. So the signal that you get out of this tells you how the photon number that you had in your pulse. And you can still recover it without destroying it in this type. But quantum non-demolition measurements are a difficult thing. Okay, but it exists. This type of translation between different modalities of qubit is possible. And so so this is how you would do a non-demolition perfect photon number measurement, and this is how this attack would work. Okay. And so this is an extremely detrimental attack, right? What does it show is that now that we have to be very careful about how we do our analysis. Let's go and see how the analysis will change now that we have this, how the BB84 protocol needs to adapt to this photon number splitting attack, and what are the possible solutions. So what we know now is that the quantification of the information leaked to Eve, okay, in this particular case, now must take into account the fact that it will depend on the number of photons n that are present in Alice's pulse. Essentially, that's what it means, okay? So we're going to try to quantify the information of Eve, okay? Of the information that Eve gets out of the protocol. So the first point that we need to make is that when, which is going to be a function of the n, okay? When it's 0, it's going to be 0. We're going to say that the information that Eve gets when there is 0 photons is 0, okay? When there is 1 photon, then we have the usual security analysis for BB84, okay? So this is going to be something that is going to look like this. I hope the notation is not too different from what you saw in the lectures on the usual security analysis. Here, I'm going to be writing it like this. So this is the entropic quantity, where this is important to note here. The epsilon here, epsilon 1, is the qubit, okay, the quantum bit error rate, on the single photon pulses only. Okay? So there is now, because of this dependency, because on the single photon pulses only, okay? So this is not the overall qubit, the quantum bit error rate that you have seen, I think, in the security analysis of BB84. This, we now need to make this distinction when we do the security analysis for in the presence of this attack, where Eve can use the number of photons, because then this will change a lot the analysis. And then you need to assume that everything that with n bigger than 1, she gets full information for n greater than 1. So this is a little bit how the information that Eve gets can be understood. So the total now of the information leaked to Eve needs to be calculated over pulses that lead to a detection, okay? And so we're going to define this quantity D, this event, it's not this event, which is a detection event. So this is event pulses detected. Okay, this is going to happen with some probability D, okay, with some probability D, sorry, a probability of device detected. And this is also known in all these photon number splitting, decoy state protocols, and all of this is known often, you can see it as gain as well. Okay? So this notion of gain that we symbol with a symbol Q, okay? So we're going to be seeing this notion of gain, which is denoted as Q, which is, in this particular case, this Q is the probability of a detection event. And you're going to see afterwards that it may depend on other parameters. Okay, so now that we have this, we can calculate the total, maybe I can write this here so that we don't go off. Total detection, the total information leaked to Eve, okay, which is going to be, you need to maximize over all possible strategies of Eve, okay. Okay, this is this expression. So this the information leaked to Eve, I repeat here, we need to maximize over all possible strategies of the adversary of Eve. And so we're taking this summation, which is the probability of having n pulses given a detection event. Okay, so it's a little bit, you'll see, we'll work a little bit with the probabilities. And it depends as well on the leaked information to Eve, depending on this n. And so this can be developed with Eve. We have maximum. Overall, we are going to be splitting the cases okay, all I've done here is that I have used this, what we said before. So the 0 was 0. For 1, we've split it and it's h of epsilon 1. And this one is 1 for all the cases where there is n is bigger than 1. Okay? So this is the leaked information. The total leaked information of Eve is given by this expression. Okay, and this you can analyze it a little bit even more. Okay, I'm going to just maybe. Okay. This one is replaced. Okay, everybody agrees? And replace this one by this one. Okay. Essentially, it's everything except for the 0 and the 1. And this is finally giving you okay. Yes. Okay. So this is the full expression. Okay, this is the final expression for the almost final expression for the information linked to if. So now the optimal strategy is that you can see. It can be shown that the optimal strategy of if is now naturally, I think you can even think about it, you can see it immediately, to block all 0 photon pulses, okay, because they give here 0 information, and to forward all multiphoton pulses, okay. This is what she wants to do. What does this mean in practice? What is essentially what is written here? So if the n is bigger than 1, so she will always perform her attack and send to Bob the rest of the pulses. In all the other cases, in 0 photon pulses, she will pretend. Okay, she will block the 0 photon pulses. So what does this mean? What does this mean? It means that we must assume, okay, given this expression here, that the probability of equal to 0, okay, this is very easy to show from we must assume, okay. This is directly derived from this because it seems this is easy to show from the base rule because of conditional probabilities, because you see that the probability of detection event giving a 0 will be 0 because we block all 0 photon pulses. Okay, so this is easy to show, and then the probability of P given n is 1 for all n bigger than 1. Okay, so we always give there is always a detection event when n is bigger than 1, and so by assuming this optimal strategy, we impose these conditions, and so by analyzing, so by applying them to this expression, you come you can calculate. You can calculate. Okay, I'll do the full derivation and then we'll see. Okay. Okay, so and so now because of course we have P. Of course, the probability by the law of probabilities, this has to be equal to 1. We can show that the probability of 1 over d is going to be 1 minus this. Again, Bayes' rule. Hope you like probabilities. Okay. And then This one is 1, right? This one is 1, so we have 1 over 2. We're calling this delta, okay? This delta, and it shows you this probability of having one photon given a detection event is given by this expression, this 1 minus 1 as my delta. So this delta parameter that is involved in the calculation of photon number splitting attacks is super important. We're going to be using it throughout this analysis, and is essentially, this is the fraction of qubits, okay? The fraction of qubits, the tagged qubits, this is how we call them, that have to be considered insecure, okay? Because they essentially represent everything that is greater, that is bigger than one photon per pulse, okay? So this is the fraction of tagged photons. This is how we call this delta. Okay? So essentially, this shows you the probability of having. It's a very natural now that you think about it. It took us a bit of time to derive it, but this probability of having this one photon event based on the detection is everything except when you have this fraction of photons that correspond to multi-photon states. So we need to consider them insecure, and essentially by a very similar analysis, one now needs, there is two important things that one needs to calculate when you do security analysis based on this type of things. It's the quantum bit error rate and this gain, okay? This gain, or as we're going to be calling it later, yield. So now, if we want to calculate with the same way the quantum bit error rate, which will allow us to calculate the secret key rate, yeah?
What's Q?
What did I do?
Q, what is...
This is the gain, sorry. I remind you here, there's too many notations, but
Oh,
it was
okay,
here.
I forgot.
It was here. Okay, yes, sorry. There's too many notations. I know, takes a bit of time to okay, does this make sense? The probability of detection.
Yeah.
Okay. So we normalize often with this quiz. That's why it's a fraction. It's a fraction of all the things that are among those that are detected, those that are insecure. Okay, it's a fraction bit. And I think there was another question.
Oh, it was the same
It was the
question.
same. Sorry, it was hidden in the thing. Okay. All right, and so last, I promise, before we go to the secret key rate, last thing to show the bit error rate. Okay, so the global bit error rate we are going to do here is going to be the probability of an error based on given a detection event. So this is obviously going to be a probability. Again, we're going to split it. As in all cases, because everything is dependent on the number of photons in analysis pulse, we need to split it in 0, 1, and bigger than 1. Okay, this is essentially what we do all throughout this calculation. N equals 0, d plus p of error, n equal 1, given d plus. This is exactly what I did before, so I'm doing it again. And bigger than 1, giving t, okay? And so the assumption now that we're going to make is that this is 0, probability of error when there is no photon is 0, and the probability of photon when there is more than one photon is again 0, okay? Because it has full information. So essentially this brings it down to this component. This is the one that gives it. These are the only cases that lead to errors for it, okay? Is when you have single photon pulses, and this is why you want single photon pulses, okay? So all of this is very, very natural. So we can develop it a little bit so that we can calculate it. This is the probability of error. I'm just changing a little bit the probabilities up like this times D, and you can show that this brings back to the notions that we saw. Okay, so this is the, remember here, this I had defined here. It is the qubit specific on single photon pulses, which I told you that this is what matters, okay? The qubit on single photon pulses times this fraction, okay? This probability of one event is the same one that we calculated above. And so it gives you the probability of an error. Total error given a detection event is given by this expression. So essentially, by having calculated all of this, by having calculated as a function of these events, the information leaked to Eve and the probability of error, which again is related to how much the probability of having a single photon pulse in its single photon state analysis pulse, essentially has given us this expression that now will allow us to calculate the secret key rate. Okay, the secret key rate is going to be, I don't know what is your favorite way of measurement. Okay, we're going to put it R. Okay, is going to be given by, okay, this is the Q, the usual factor, the shifting factor. Okay, shifting factor. So the probability that the bit is going to be kept for shifting, then the probability of detection, which is the gain, again, and then according to okay, I'm just using the usual expression for the secret key rate, okay? The secret key rate here, so if you consider that this is a binary symmetric channel with some imperfect error correction, okay? Here I'm going to assume that you know what I mean. Hopefully you saw that, okay? This will be equal to 1 minus some factor for the error correction and the entropy, which is a function of the full error rate, okay? And then the whole point is to see the leaked information to Eve, and now we really have everything that we need to calculate this. Remember, it was given by this expression here, okay? And we can now calculate it, the information leaked to Eve, by everything that we have calculated up till now. This we have calculated that it's 0. This one is 1 minus delta, and we have also calculated this expression from here. Okay, from here, essentially, you can derive that epsilon 1 is epsilon, the full Q-bar, divided by 1 minus delta. Okay, this is the Q-bar of single photon states can be given by this expression. The fact that we have calculated the full Q-bar to be equal to this gives you that the Q-bar for single photon state is the full Q-bar divided by 1 minus delta. So essentially we have this expression as well. Okay, we have this expression as well. We have calculated this, which is 1 minus delta. We have this one is 0. So we have an expression for the information leaked to Eve, and we can put it all in here. Okay, we can put it all in here. And so what is the expression that I find for the secret key rate, the final one? If you put things together, again, this is the gain. Okay, I remind you, the full gain is going to be delta and this is the full expression, okay, of the secret key rate, okay, for in the case where we are, essentially we are subject, where our protocol is subject to photon number splitting attacks, essentially, which means that it has this introduced this dependency on this delta factor, which is the number of, again, of tagged qubits, photons. So it's essentially the probability that we have this this dependence on the number of photons inside the pulse of the pulse of Eve, because Eve can exploit it. Okay, this is how it changes the secret key rate in when you take into account these photon number splitting cases. Does this make sense? Thomas, yes.
Yeah, just a small clarification. So the numbers that you're considering,
Yeah.
that's the numbers, the number states coming out of Alice, right? That's so the channel loss and detector losses that comes later.
This essentially, what is hidden inside what I've said up till now is, for the moment, the detector imperfections inherently are given to Eve as well. Essentially, by giving expressions like this one, by saying, for example, by imposing this, that the detection event when, by imposing this, by the detection event when the n is bigger than 1 is always 1, okay, essentially, and that the information gain for Eve is always 1, essentially when n is essentially I have included all these imperfections and I have given them all everything to if. So it's a very conservative, yeah, it's a very strict definition of security. Yeah. So one, indeed, yeah, we are going to introduce a bit losses afterwards, but essentially it means that this photon number splitting attack already, by doing all of this, I have already essentially considered that everything is perfect, that if has already replaced the lossy channel with the perfect one, and also she can control fully the detector imperfections. That's why they don't come at all into the picture. It's a very conservative, yeah, it's a very strict version of security. It's the worst case scenario. Let's put it that way. Okay.
Okay.
So indeed, so essentially, so this this PNS attack, this photon number splitting attack, is particularly detrimental for high loss channels. This is exactly what Thomas tested here. So it's particularly detrimental for high loss channels. Okay. So. Maybe we can show this a little bit here. Why is this the case? Well, because so as this is exactly the point that Thomas is making as well. As we know, the quantum channel, we haven't talked about it at all yet. We have discussed about the other elements, but not the quantum channel. Is characterized by a transmittance. Okay, it's characterized by this transmittance. Okay. Efficiency, so it's probability that the photon that exits Ali's side reaches Bob's side. Okay, so it is a transmissivity essentially of the quantum channel. And so, if you want to have, if you look at this expression, if you want to have a positive secret key rate, you have to have a delta for R that is bigger than 0. You have to have a delta that is smaller than 1. Okay, you have to have a smaller than 1. And so now if we consider what's happening in a realistic scenario, the probability, the Q, okay, the gain, the probability of a detection, event is going to be something that is proportional to mu and t. Okay, does this make sense to everyone? What have I written here? The probability of a detection event is going to be proportional to the average number of photons per pulse. Multiplied by the transmission efficiency. This is essentially what arrives at Bob's site. Okay, so the probability of detection is going to be something proportional to that. While by the Poisson distribution, we know that this is going to be something that is proportional to mu squared. Okay, to mu squared. So we have, if we put everything together with a definition of delta, you remember here, that's the definition of delta here. This essentially tells you that delta is going to be something that is, I wrote it again here. It's going to be something proportional to mu squared divided by mu t. This is mu divided by t. So if you want delta to be smaller than 1, this means that you want mu over t to be smaller than 1. Okay? And this essentially means that you want mu to be something. Okay? You want, and this is super important. This basically essentially tells you why photon number splitting attacks are so detrimental for the QKD. What does this mean? Is that the Alice needs to adapt the average number photon of pulse that she's sending to Bob to the transmission efficiency. When you have high loss channels, this transmission efficiency transmittance is small, so she has to reduce mu to counter, the attack, the photon number splitting attack of Eve. Reduce the probability that there is multi-photon pulses proportionally to how much transmission efficiency she exploits, because she replaces it with a perfect channel, right? And so this essentially means, and when you reduce mu, it means that you increase the zero photon clicks, the zero photon events that give you no information. So essentially this, what it means, that you get a scaling, you can easily see that you get a scaling of your secret key generation rate that is on the order of t squared. Okay, so this, you get a quadratic drop square, the quadratic, the secret key generation rate drops quadratically with the channel transmission, and this explained, remember what I just said at the very, very beginning, I showed you the graph with the different scaling, you know, with a laser source and with a single photon source. This is exactly what it is with a normal single photon source with a perfect, where you don't have this 1 minus delta, the rate is proportional to Q, and so it's proportional to mu times T, okay? So you have a linear dependence to the transmission efficiency because mu doesn't change, you know, you can consider it fixed, okay, in normal scenario. While here, with the photon number splitting attack, this mu changes with the T, as we saw here. So this gives a quadratic scaling to the transmission efficiency, and this is why it's so detrimental. Essentially, it means that your key rate drops completely abruptly with the transmission efficiency, with the transmittance of your channel. Okay, and this. Maybe that's a good point because I was going to go to decoy state. So maybe we can do the break now? Yeah? Okay, perfect. Okay, so I realized that there are too many things that I want to tell you. So I'm going to go even faster. As you noticed, so I'll go a little bit faster than I thought on the decoy state so that we have a little bit of time to discuss about some other stuff as well, because I really want to talk to you a little bit about measurement device independent and side channel attacks, etc. Okay, so I'll try. So I think you go to the main picture now. Okay, you go to the main picture, you got the idea of this photon number splitting attacks. So essentially, so you understood why I hope this is an important. So it obliges, as we said, IS to reduce the average photon number per pulse proportionally to the transmission efficiency of the channel, and so therefore this affects, as we said, drastically the secret key generation rate because of this dependence, quadratic decrease. So what is the solution that the researchers found to answer to this? It's the so-called decoy state. So in order to understand this a little bit, I'll show you a little bit the idea behind it, then how you can model kind of the QKD system, and then this will allow us to show you a little bit how these rates look like in practice. So to understand how to get a little bit of a gist of how this decoy state protocol works, we need to retake the expression for the secret key generation rate. So this, what I left here, is the final expression when with including the photon number splitting attacks, but we can also consider it from essentially the very beginning here. A notion that becomes important is this, which is linked to all the quantities that we introduced before, is this notion of the yield, okay? Notion of yield, which is defined as it's given for the N photon component of the state, and is given as the probability of having. It's given by this expression, okay? Given the probability that we have a detection event, given conditional, okay, that Alice had sent an N photon pulse. So this is a quantity that is important, and of course, the other quantities that are important are the N photon error rate, okay, that we can look like this. The N photon error rate, we saw the example for the single photon state before, that can be written as the probability of getting an error. Okay, getting an error given given a detection event and an N photon state. So these are quantities that come a lot into the analysis of this decoy state protocols. So it is possible. I'm not going to show you the derivation to save a little bit of time. It is possible to understand it a bit better, to rewrite the general expression for the secret key generation rate that I wrote at the very beginning, like this, okay, where we have here the shifting, and whoever is interested, I can show you this derivation, where we can write it as see here we have the yield corresponding to 0 photon states, where we need to calculate a lower bound, okay, with a probability of having 0, okay, the probability of the yield of having an n photon state, again with a lower bound with probability for 1 photon, and this is going to be, as always, multiplied by the security generation rate, where this one has to be an upper bound, okay, for the E1, here, and then minus the gain, the overall gain that we defined before, and the parameter with the full. Okay, so this is an expression that is kind of linked to what we said before. It's essentially the same one, except that you have rearranged a little bit things so that you can see it in terms of this yield and of the specific, in this particular case, is the 1 photon component of the QB, of the quantum bit error rate. So what is actually measurable in a state, in an experiment like this, or in an implementation like this by Alice and Bob, is the probability of the detection, okay, the probability of the detection, the overall gain of the protocol, and of course the overall quantum bit error rate, which is the probability of having an error given a detection event. And of course, they have the statistics of the source, and this is going to be particularly important in these decoy state protocols. And given all of this, they need to somehow bound these values that you see here so that they can calculate, they can estimate how much information has linked to Eve. So they need to somehow find a lower bound for this yield, okay, the 0 photon, for the single photon, and also upper bound the quantum bit error rate that is upper bound the quantum bit error rate that is due to single photon states. And this is the part that I'm going to skip a little bit. Based on all the analysis that we saw before on how photon number splitting attacks work, you can actually calculate these bounds, okay, and you can find them to be, okay, and this you have to believe me at this point, okay, that this is 0, but it's kind of linked to what we said before, right? This is equal to 1 minus delta, and you remember delta, right? This is the fraction of tagged photons, the fraction of photons that we saw that can be considered insecure, divided by P over 1, and then this is equal to okay, which is what we saw before as well. And so a specific characteristic, a very property of the photon number splitting attack that we saw before was that Eve could take advantage, could adapt her attack to the n, okay, to the number, to the photon number that was in the pulses that were then the pulses sent by Alice. Okay, so this is how this operated. Okay, so now we need to consider that all these quantities here, the yield here that is a function of n, and the yield for a particular n photon state, and the quantum bit error rate that is also a function of specific non-photon state, are all under the control of Eve. But by doing this clever trick that we're going to see for the decoy state protocol, what happens is that Alice and Bob can recover their advantage by introducing a more complex statistics, okay, in the photons that are going to be sent to Bob. So what's going to happen is that Eve, thanks to this clever organization of the protocol, will not anymore be able to adapt her attack to the photon statistics, because she will not know the way that the protocol is constructed. She will not know beforehand what these photon statistics are. This is essentially the bottom line of this decoy state protocol. And this is what will allow Alice and Bob to improve essentially these bounds and to make them very close to the nominal values, the yield 0, 1, and the epsilon 1, and therefore this will mean that it will not be necessary anymore for Alice to adapt the mu to the transmission efficiencies. You can use a fixed mu, and we recover essentially the linear scaling of the secret key generation rate. So what is the protocol that Alice will use? She will randomly choose, okay, so Alice randomly chooses photon statistics within 4 pulse. Within a set, okay, within a set that contains the mu, which is the nominal value, average photon number per pulse that we will use for the signal, but also a set of mu, okay, and these are what they are called the decoy states. Why do you call them decoy? Because they are essentially the trap states, okay, that they are the ones that are used as traps to prevent Alice, Eve, from being able to exploit these photon statistics, this number of photons in the pulse, as we said, to perform her attack. Okay, and this follows some probability distribution sigma, okay, probability of sigma, and she sends, what Alice sent is weak coherent states, okay, where she chooses for each pulse randomly among these, within this set, her photon statistics. And so what's happening is that after Eve has interacted with all the pulses, Alice is going to send it to Bob the information about these statistics, okay, what she has used, okay. So and then and so this means that Eve, as I said, cannot adapt anymore her attack to these statistics, and this essentially means that these quantities that are so important here, okay, that appear in this expression, the yield and the yield and the n photon states, do not depend anymore on sigma, okay. They cannot depend anymore on the statistics that has been used for the protocol, and this is crucial, okay. This is crucial. It essentially means, as we said, that Eve is not able anymore to adapt her attack. Okay, this is essentially the bottom line of how this works, and it can be shown with only 2 decoy states. So essentially mu and a 0. Okay, so if Alice uses in the set only her signal average state, one single decoy state with number mu that is smaller than mu, okay, smaller than mu, and a 0 vacuum state, okay, this set, you can show that essentially Alice and Bob can calculate these bounds that are very, very close. The bounds become very close to the actual values, okay, to the actual values, and as I was saying, this means that mu can be considered now almost, you know, a fixed value. It's not anymore a function of the transmission efficiency, and therefore for all t, and therefore we recover this linear independence of the secret key generation key generation rate as a function of the transmission efficiency that we had for a single photon source. Okay. So this is the general idea behind this protocol. It actually looks simple, right? I mean, you had to think about it. It's just basically blur the photon statistics, so it's not impossible anymore for Eve to decide, you know, on its end what she's going to do. She cannot do this anymore because she does not know, because it's picked randomly. She does not know which is the photon statistics that are being used. So the parameters that she has access to are not dependent anymore on it, and that's it. Essentially, we recover the previous statistics. So what I'm going to do now is to model, to see a little bit more formally how you can model this QKD system with the decoy state, so that we can actually calculate as a function of the parameters the secret key generation rate, and draw the lines. Okay, so if we model the QKD system. as we tried before. So we said we have a source, okay? This kind of brings together everything that we have been discussing. We have phase randomized weak coherent states. Okay, phase randomized weak coherent states that are sent. There is an incoherent mixture of photon number states following a Poisson probability distribution, okay, where the Poisson probability distribution is given by this Pn, where sigma is the photon statistics that are used in the different types of states that are used in the protocol, okay? And these are picked, as we said, randomly. We have a channel that has its transmittivity E, and we have the detection system, which includes a measurement setup that is used to decide where the photons will go, okay? This includes, and the single photon detectors themselves. And this is quite simple model. If you think about it, it's not very complicated. It will be sufficient, sorry, and the detection event, this time we're going to include them explicitly. We're going to include the properties of our detectors that are the quantum efficiency and the dark count. And so now what I want to do is that I want to model this QKD system. The simple model that you see here will be sufficient to be able to estimate the parameters of a system and be able to plot, okay, what is the expected performance of a system that uses these decoy states, and then compare it with this expression here, which is the expression of normal BB84 state implementation that is subject to photon number splitting attacks. So what we've seen already, okay, is that we have the gain here that is a function of the photon statistics. So this gain is going to be the probability of a detection for the specific sigma. Okay. This is going to be, I'm going to condense a little bit the derivations. I'm going to go to the final result without going through all the different steps. Just a little bit of time. So this is going to be the average of the yield over the yield where, I remind you here, the yield. Like a bit bringing everything together, okay? So this is the gain of the system, and this, if we want to estimate, this yield here, okay, it's going to be an estimate, a union of two independent events, okay? Estimate in my model, and this you will recognize it. It's going to be the real clicks, okay? Together with the dark ones, the non-real ones, based on them. Okay, so the real events, sorry, what did I do here? A bit of an issue with notation, okay? And so this we're going to okay, now it's a mess. All right, can you see it? Sorry, I was out of space. Okay, so this is the union, okay, of the events where we have a real event, a dark count, okay, as a function of condition on n photons, so this is the yield, okay? And so I've just quite simply split the two events, the probability of the real one, probability of a dark one, okay, minus the multiplication of the two events, okay? So this is what is written here. And so now, if we want to move to link it to real quantities, okay, what we're going to do is that we're going to call this the probability of having a real event. We're going to define it, okay? We're going to define it as this quantity that I'm going to be calling it n, okay? This one is simply the yield of 0, okay? And this one is the multiplication of these two. And so if I want to put them together, if we say that this dark gown event is much smaller than 1, which is typically satisfied in practice, we can just say that this is equal. Okay, so this is the yield of an n photon state. Is this the real plus this dark gown? This dark gown probability, this essentially zero photon, the zero photon probability, or you can call it dark gown. And so if we want now to calculate in more detail this parameter here, so here, as we said, it's going to be the probability of a real event based on an n photon detection event. And so this, we're going to introduce the loss now of the channel. So when it's happening, this is the probability. What is the probability of getting a detection? Is the probability of not getting a loss, okay? Of not getting a loss of the n photon states. And if we consider that all photons, are lost independently, this is going to be, I just finish this and then this is the probability of each one of them being lost separately, okay? And this is equal to the probability of each one of them being lost separately is given by this expression, where eta t is the quantum efficiency and the transmission efficiency of my channel. Yes.
So when you get rid of this y0 tilde, because it's like really close to 0, how come you keep the term on the right hand side like the?
Yes, that's a good point. I want to make it smaller than here, smaller than 1. Okay, yeah. So we can remove it from here. Yeah. But I mean, this doesn't tell you how it compares with this one. Okay, yes. So it's smaller than 1, but it doesn't mean that it's smaller, much smaller than this one, right? And so you need to keep it.
Oh, okay.
You cannot get rid of it entirely. Is that your question? It's smaller than 1, but I don't know how it compares with that one, so you cannot remove it completely. Yes. Okay. And so this is the expression of the probability of having a real click. And so if we write all of this together, we can estimate the gain for the new. Can estimate the gain for the new photon statistics as being, and again, I'm not going to go into the details of the calculation, already it's complicated like this. Okay, so it's given by this expression, while, and we can also calculate we can also calculate the error. Okay, now I think you have been, up till now you have believed me that we can calculate all errors and yields and gains that we want. Yes? What is
when you calculate the efficiency?
It's the probability of loss. Which is the loss.
Okay.
So it's essentially what have I written here is that to get a detection event from a real photon, it means that you haven't lost your photon. It's 1 minus the probability of losing your photon. And then assuming that each one of the lost photons is lost independently, you can just, this is just the, to the end, the probability of losing 1 photon to the end. And so the probability of losing 1 photon is the probability that it doesn't get transmitted, okay? And the probability of being transmitted and being detected is eta t, which is the transmission of the quantum efficiency, so the probability of losing it is 1 minus eta t. And so it leads to this expression, okay? For the click, okay? So these are the real, let's say, clicks in your system, the real cases where you detect a real photon. Okay, and so, and then afterwards, you want to calculate. You actually wanted to calculate your so you have gotten, based on this, you have gotten the expression okay. So this allows us to calculate this yield, okay. This yield. This allowed us afterwards to calculate. So I didn't show all the steps, but based on this result, I've taken this expression now, okay, and I have estimated the gain for specific photon statistics mu, okay. This is what this shows. It shows how to go from here to here. Okay, and now I have my gains, I have my yields. What do I need? The errors. Okay, I need to be able to estimate my errors. Remember here that what we care about is the errors. Did I write them? Yes, there we are. Okay, this n photon error rates. These are the ones that I care about, and I would like to calculate them now. This. For my model, for my QKD system model, where now that I have included, you know, all the parameters that are important. So to be able to calculate this epsilon n here, which is my goal. So I need to calculate first. I need to first calculate this joint probability. So I'll keep this. Okay. So this has been calculated. We keep it. And I need to calculate this error probability. This is a joint probability. This is joint probability, and this is again two events, okay, that you will recognize. These are the events estimated. These are when an error occurs, okay? When there's an error occurs. When there's an error occurs when there is a dark count, okay? And so this corresponds to this case. And here, this epsilon 0 is going to be considered equal to 1/2 because all dark counts are considered to be completely random, and they can create cliques in both. And they can create errors with half probability, okay? While this one here, this expression here, okay? This is the probability that the pulse goes to the wrong detector. So this is a probability that you have a real event. Okay, this is a probability that you have a dark count, and what errors it creates. And this errors is 50% probability that you will create an error. This one is the probability that you have a real event, a true event. And then what happens? When is an error created when you have a real event? Is when it goes to the wrong detector. So what can lead a photon to go, a pulse to go to the wrong detector? It can be source flows, it can be encoding flows, it can be different imperfections in the system. Okay, so this can happen to the wrong detector, and also what you can see in this expression is all these events are considered mutually exclusive. Okay, this is important assumption that we consider here that all of these are mutually exclusive events. And also that the probability that an error occurs when there is an n photon pulse does not depend on n. Okay, we consider that the probability of going this error detector is considered this going to the wrong detector is considered kind of constant, independent of how many photons you had in your pulse. So this is also, I'm just pointing it out because it's an assumption. So it's considered fixed, and typical values that you can find in the practical implementations is on the order of 0.5 to 1%. Okay, just to give you a little bit of an idea of what type of values this type of errors can take. Okay, and so once we have calculated this, then this allows us to calculate our error. Okay, because we can take now an epsilon n. It's a probability, as you see here, of an error given the n, which can be used. Can be written as the two probabilities that are written here divided. Okay, and putting all of this together, again, you need to believe you came up with this expression. This is expression for error, and you can show, and then you can show that the full that the full bit error rate for specific statistics mu, it will be given, and this is, I think, almost close to the final expression, given by this. That's it. That was the second expression that I really needed. Okay, these are the two expressions that are really useful: the gain for the specific statistics in Q or QM, and the overall error rate, the QBER. Okay, for this part of the photostatistics of M, and you have expressed them. You have this in this expression here, the function of parameters that are accessible. Okay, that are accessible in the system. You see the average photon number per part, the quantum efficiency, the transmission efficiency. These quantities that are experimental, that are like determined. These errors that we see in going to the wrong detector. This dark count error, and so these are all quantities. Okay, that. And you see here, these are all quantities that we have modeled in our system. So we have kind of managed to write this expression that are entered into the secret key generation rate as a function of parameters that are accessible experimentally. Okay, and so this is important because now we can go back. We can go back to our secret key generation rate, okay, and we can write it. We can write the final expression, which is close to the one that I have written here. Do I have it? Yes, that I had written here. Okay, so this is the expression for the secret key generation rate. The secret key generation rate is a function of. Secret key generation as a function of all these parameters for this decoy state protocol. So now what I'm going to do is that I can compare the case where I have non-decoy, like here, with the case that I have decoy states. Okay, decoy states, and this final expression can be written as, so we always maximize as a function of mu, and this is the case here as well. In the simulations that I'm going to show to you, maximized over all mu, and so this is given as this 2 mu. This is what I showed to you. So it comes inside. There you are. So these are the two expressions for the secret key generation rate with photon number splitting attacks and for the decoy state protocol. And now we can see how these look. I can show you the graph. So this is a simulation where you can actually see exactly the expressions that I just showed to you. Okay, that I showed to you. For the two cases, and we recover exactly the statistics like the scaling that we saw before, where you see that without the decoy state, this is an expression for specific numbers, so that you know in this simulation that were done by these wonderful people in our group. And so we have a secret key generation as a function of channel losses, so you see that we have, what are the numbers that we have used? So the shifting parameters is 1/2, quantum efficiency considered 10%, this dark count rate 2 times 10 to the minus 5. Okay, so these are numbers that correspond to single photon detectors that are usual avalanche photodiodes. Okay, the error rate that we saw here, the epsilon d, is for the wrong detector when there is a real event is 0.5%, and the f for the error correction, the factor for the error correction is considered 1.2. Okay, and the losses, and this is important, the losses, as always, are modeled as like this. For the experimentalists among you, this is obvious, but still, maybe I should point out to everyone here that the losses here are linked like this to the transmission efficiency. This is why you see here a scale, in dB scale for the channel losses. Okay, so often the losses we use them in dB, while the transmission efficiency we can also link it to the distance as well, depending on the losses per kilometer that you have for a specific experimental implementation. So often when you see secret key generation rate as a function of distance, you see it in kilometers, and this must assume some sort of coefficient between the losses and the distance. Okay, and in real life, and this will depend on the wavelength of your communication. Sorry, I'm doing a total experimental little point here. This depends on the wavelength, and so in telecommunication wavelength, which is the usual one used for fiber optics, for example, you will get a loss coefficient that is equal to 0.2 nominal dB per kilometer. So you can take this dB here, you can adjust it with this coefficient, loss coefficient, you translate it into distance, and so you can plot as a function of kilometers as well if you prefer. Okay, so this is easy for fiber optics. It's more complicated for free space optics, but I'll let Thomas explain all of it tomorrow, because you don't have a fixed attenuation in your free space channel. And so this is the type of rate that you get for the decoy state protocols, and this is what revised DB84 essentially some years ago, and it has become now really the reference protocol for QKD, even when using lasers, okay, when using weak coherent state. And despite the fact that there was this photon number splitting attack that kind of felt like it would destroy the performance of the protocol, by introducing this decoy state idea, which is like a very smart idea, right? It's very simple, but very smart, and you can see how it works. It has essentially become the reference. It's by far the most mature protocol today against these photon number splitting attacks. Of course, as we will see right now, there is other protocols. Like continuous variable QKD, this we're going to see a little bit later, that are not, this is not single photon based protocol, so it's not subject to photon number splitting attacks. And there is also the whole category of what is called measurement device independent type of protocols that I'm going to show you a few ideas after looking a bit at the side channel attacks. So this concludes this part of photon number splitting and decoy state. If you have questions, it's a good moment, although you can think about it, of course. So we can move on to a little bit other things. I hope I didn't completely kill you with all these gains and and errors, but I hope you kind of understood how it works. Okay. Okay, so let's move on. So essentially, these photon number splitting attacks were the first example. We didn't know it back then when they were involved, but they were kind of a first example of how you can have a deviation between a security proof and a realistic implementation. And we found a solution, but there is a whole category of cases where such deviations may occur. Okay. These are called, as we said, side channel attacks. They are crucial. They exist in the very, very beginning of the field. I have here, and maybe some of you have seen it already, the very first system, that QKD system that was built. So it's kind of an old device that was used, that was built by the teams at IBM and University of Montreal, where Charlie Bennett and Sil Prasad were, and it was written, as you see here, that the information is secretly over a distance about 30 centimeters. The legend has it that they were extremely, system was extremely vulnerable to side channel attacks in the sense that this modulator that you see here, this is the one that picks the 4 BB84 states, was extremely noisy, and it was making a different noise for its polarization that was selected. So it would have been enough, the legend says, to listen to the device to be able to hack it. Okay, but it actually shows that there is a big, honestly, there is a big gap between what you do in practice and what happens in real life. So there is lots of efforts today everywhere in the world to systematically go through the different attacks, the practical security of QKD systems. You know, we saw that in practice. I'm sure you were convinced by the security proofs that you can have ideal security, but realistic implementations are faulty, okay? And so this is a problem because you cannot anymore prove the ideal security that you would like to have, and so this does not help for the use, or for the widespread use of QKD technology, right? And in particular for the certification of this technology that has become a big challenge today. So there are huge efforts in Europe in particular. There is a big project that is called Nostradamus that has as a goal to go through every single side channel attack that is known for every single QKD protocol, okay? Analyze it. There has been, as a basis of work, there has been a very extensive effort of the German security agency that has published a comprehensive list of all the implementation attacks that you can have in different systems by classifying them in the severity, in the importance, on which part of the protocol is attacked, and which system, which part of the system that I showed, the generic system that I showed, qubit encoding, channel decoding, detection, and classify the severity and how the countermeasures and everything. So there is, just to point out that this is not a small topic. So maybe to give you I want to give you a couple of examples. So what we saw, for example, you can see in for a BB84, you can have the component, okay, the security proof, security assumption, sorry. The realistic implementation, practical setup, and the practical setup. And so you can see, for example, the photon source is one of the components, and this is the whole work that we've been doing for the last 1 hour. The PNS is linked to that. The security assumption here is, of course, that you have perfect single photon. This is not true. You have a coherent laser, okay? And this is exactly what we have just discussed for a long time. But you can also have lots of other components. You can have, for example, issues in the encoding state. So the encoding of the protocol. So you can have, for example, the security assumption is that you have 2 dimensions, for example, in your case, for your qubit, while in practical setups you cannot certify this, you can have arbitrary dimension, okay? Or you can also have a basis independent that you can actually encode. You can encode the qubits, okay, in the orthogonal modules, we're saying, of the electromagnetic field with a basis independence, while in practice this is not correct, and you have flaws in your source. And same the decoding as well, the measurement setup. You can have exactly the same problem. You can consider that you have 2-dimensional, but in practice you can never certify this, arbitrary dimensions, and also basis independence, okay? While independence, while this is not true, and you have detection flaws, okay? These are like a very global and generic categorization, and more specifically, so this is the measurement setup and the single photon detector. the single photon detector, you can consider that it's ideal, while in practice it's a threshold detector, which we discussed before, which means that it cannot tell you if there is more than one photon number, okay, which is linked, more than one single photon that is hitting the device in particular. So all of this, like it's a bit of collective description of what security assumptions are the most common that are not satisfied in practical setups. So we discuss this again. Maybe a couple of more that I would like to discuss is mostly I'm going to focus on the detection because this is by far the most vulnerable component of a QKD system. Why is it more vulnerable? Because it's at the end of the chain. Let's say it's after the quantum channel. So essentially what it means is that Eve can input information, can input whatever states she wants into the detectors, into the measurement, the detection setup. And she can use this information to perform her attack. Okay, so this has received the most focus of attention for the side channel attacks. But we should not forget that the other as well. So I'm not going. So the photon source we said, but there is also an issue. For example, that the phase randomization. I told you when we discussed about it that I was going to come back to it at the point of the side channel attacks. There is in particular an attack that is called non-random phase attack, and again this is particularly important because lots of experiments, being an experimentalist myself, I know it, sometimes we say yes we could do it, but we don't actually do phase randomization. This is important because essentially what happens is that if you don't phase randomize the coherent states, Eve can perform an unambiguous discrimination attack. Okay, she knows she can kind of discriminate the coherent states that are coming out of them. That are coming out of the laser because they have a specific, so you haven't scrambled the phase reference of these coherent states. They are not an incoherent mixture of states, and therefore she can actually, because these coherent states are pure states in that case, and so in that case she can perform an unambiguous state discrimination attack and retrieve all information from the system. Other type of important single side channel attacks, as we said, single photon detectors. So one interesting attack is the one that's called double click attack. So you have some probability of both detectors in your system clicking at the same time, right? This can happen, as we said, for many reasons, because we had the Poisson distribution. Sometimes it can happen, the probability is low, but still it can happen that a double click event occurs. And the naive response to such an event is to do what? Usually to say, discard them, exactly. So this is the naive response that you would want to discard them, but in fact, this is a very naive and incorrect answer to it opens the door to this important side channel attack. Why? Because what happens is that what Eve can do in this tuple, so she can perform, she gives a very high advantage to Eve because she can perform a normal intercept and resend attack. Everybody here knows, you discussed intercept and resend attacks when you did the security. No? Discussed? Not discussed? Yes? Some people say yes, some people say no. So, I don't know if you remember. So, intercept and resend attack in BB84, just a little summary, is like when Eve gets into it's the most, the simplest attack Eve can do, right? She interferes, she stays in the quantum channel, picks all the pulses, okay, performs a random measurement in one of the two bases, and then, depending on the outcome that she has measured, she sends the corresponding state to Bob, okay? And when she has picked the correct basis, the attack goes unnoticed, and sometimes with some probability, 25% probability, maybe you saw this, it can lead to an error, okay? So this is the most standard, the simplest, let's say, the intercept. So she can perform the intercept and send the attack, but she can also, by randomly choosing the basis and everything, but she can also at the same time send a strong signal in a Bob setup, okay? And so what happens then, if the state that she sends to Bob if they had picked the correct basis the same basis as Bob. Then, by the way that this measurement setup is working, the whole pulse is going to go to the correct detector, okay? But if she has picked the wrong basis, it will be split in two. It will create with high probability a double click, okay? This will be discarded by Alice and Bob. So essentially, by doing this, you post-select nicely for Eve all the cases where she has the correct basis. Okay, so it's a kind of, you give an advantage to Eve by discarding the double click events. So what you should do, is to apply a random, to indicate a random bit for each one of the cases, to assign a random bit to each one of the cases when a double click event like this exists. Okay. And so there is a lot of work that have happened around this that you can show that if you do this strategy, then you, by using the so-called squashing models, you can reduce the real detection system to a qubit, to a real qubit measurement, and this removes this flow that I've written here, which is a kind of uncertainty between how the security assumption of having a two-dimensional measurement fits with a real practical setup that you have. Okay, so there has been quite a bit of work to be able to include into the security proofs to reduce the gap between the security assumptions and the practical setup. Other type of attacks that are important, timing attack, okay? So what happens, like maybe these experimentalists among you will know this, that the single photon detectors are often used in what is called gated mode, okay? And this is done so that we can reduce the dark count. This means that the signal is only detected in specific time window, and there is a link between the detection efficiency and how the detection efficiency of a specific detector within this time window. So one can, like Eve, can also use these events, this detection efficiency mismatch, by moving these time windows according to her, by exploiting this gating in her system. Other very important, and I think this is the last one I'm going to mention, they were extremely, they became popular after they were done by the quantum hacker, who is very well known, Vadim Makarov. So he showed that how it's possible to hack QKD systems by attacking the single photon detectors, and this exploits the physics of single photon detectors. So here I show you two examples of single photon detectors that are the most common ones. So on the left you see the semiconductor avalanche photodiodes that are used very, very broadly, very widely for QKD applications. So these are the semiconductor devices where they rely on the photoelectric effect. Okay, so in these detectors. So when a single photon is detected, this leads an electron to the conduction band of the semiconductor, okay? And then, because you want to create this avalanche effect to make an electrical signal sufficiently big to be able to be detected, because otherwise it's going to be too low, you need an amplification stage, okay? And this creates the avalanche in these semiconductor single photon detectors. I'm going to explain in a second what this means, and then just a comment on the superconducting single photon detectors that have become right now the state of the art in terms of performance on single photon detectors. They have the highest quantum efficiency, the lowest dark count. You've understood that these are the two major performance criteria for single photon detectors. How this works? So you see here, this is a nanowire. Okay, this is a nanowire made out of a superconducting material. So the material choice is actually very important. It has maybe the nanowire a few nanometers of width. And what happens is that when a single photon is detected, it creates a so-called hotspot, a sort of like thermal, localized thermalization, it decreases the temperature, so essentially the current goes just a little bit above the critical current, so it breaks the superconductivity of the system, so the wire goes into this resistive mode, okay? And so this is what creates a big voltage pulse that can be detected by as an electric current that then creates that is a click in the superconducting detector. And this is super efficient. We have record high efficiency in superconducting detectors, but it is superconducting material for cryogenic temperatures, right? So sub-Kelvin temperatures, so you need cryostats to operate these devices. So they are not as easy to use as these room temperature semiconductor avalanche photodiodes that are very widely used in QKD. So here you see an example of this attack. So the way that this attack worked is that when you realize that a single photon detector of this type, of this avalanche photodiode, what's happening is that it's operated at a voltage that is just above the breakdown voltage of your semiconductor. So what this means is that the single photon creates an excitation. So this is called the Geiger mode of the single photon detector. And once this event happens, it goes into a quenching mode. So you put it in a quenching mode, which means that you bring the voltage below the breakdown until it kind of has the time, the material has the time to calm down, okay? So we call this a dead time of the device, and this is important because it determines over which time window you're not going to be able to receive another single photon. It's your detector is not responsive in this period, so it limits the rate at which you can detect single photons. Okay, it goes into this quenching mode, and after this dead time, it is ready again. The material is ready again to receive a single photon. And so this works nicely, but what the hackers found out is that if you send a strong classical signal into this device, it operates in this linear mode, okay, and not anymore in this Geiger mode, and you kind of you can kind of control it. So in this so-called blinding attack, so what they did is that they performed the usual intercept and resend attack that we said before, but while also again injecting strong light into Bob's device. Okay, and then if now wants here the current of her signal, of this strong signal, to be above the threshold level. You know, the threshold level is the one that allows to go into this avalanche mode, this Geiger mode of the semiconductor. So you want the current of Eve to be bigger than this threshold. Okay. Okay, bigger than this threshold for if you want it to go to a single detector. But if you want it, if it's the wrong basis, okay, if you have a different, again, same as before, same way that one I described before, you would like it to be split into the two detectors and not to be detected at all. Okay, and so this essentially means that you want at the same time to have the current of Eve divided by 2 to be smaller than the threshold detector. So this is what is shown here. Okay. In that case, in the case where when it's smaller, it doesn't create an avalanche effect. While when it's bigger than the threshold, it goes to a single detector. So if these conditions are met, if the current that Eve creates, okay, is bigger than the threshold but smaller than twice the threshold of the device, okay, this is what is the condition is met. Then what they showed is that you have a full blinding attack. You essentially control fully your single photon detector. You can recover. They showed literally 100% recovery of the secret bit. Okay, so it was a very powerful attack, this blinding attack. The countermeasure is easy to understand. The countermeasure, what you have to do is you need to put a monitoring photodiode at the input of Bob, and so this monitoring photodiode will tell you if there is a strong classical signal that is entering Bob's device. Okay, I mean, it's easy to think countermeasure, but you have to think about it before. You have to know that this attack exists to be able to implement it. And so there is, as I was telling you before, so this is type of side channel attacks. As I told you, there is an exhaustive list. There is huge number. I just mentioned a couple here. We're not going to go through all of them, but you see the idea, right? They are relying on imperfections, on sometimes extremely technically in the devices that really exploit details in the physics of the devices that we are using to be able to extract the information, but they can be very powerful. So what is the way around it? The magic word is device independence, okay? So from a theoretical point of view, if you want to not have to worry at all about this type of side channel attacks and about imperfections, you need to somehow create the conditions theoretically to not have to make as little assumptions as possible about the devices that you have. And if you don't have to make any assumptions, well then you're not subject to side channel attacks. So you will see with Rotem this afternoon all the theory behind the full device independence. Maybe Rotem will also talk about semi-device independence, which is kind of a very nice way of like going gradually into removing assumptions in QKD. And QKD and more generally in quantum information. So this is going to be based on Bell inequalities, okay, non-localities. So this is different type of math. But of course it's linked, but it's not exactly the same as we saw this morning. In the meanwhile, there have been some other proposals, and this is what I would like to focus on for the next 10-15 minutes, the measurement device independent QKD, okay, which is one way that was found to solve, to remove at least all the side channel attacks that are linked to the detection device. Okay, and so how does this work? How does this MDI QKD, the concept? The concept, I'll show you a little bit, not much derivation. I'm just going to show you a little bit the concept of how MDI QKD works. So we know already that if Alice and Bob share a maximally entangled state, okay, they can extract a secret bit, okay? You know this, right? This is entanglement-based QKD protocol. They can extract a secret bit by the monogamy of entanglement. There is also the entanglement swapping version of this that you see here, where what you have is that Alice and Bob receive one part of an entangled photon pair. The other part is going into a central node, so this is going to be really the context of MDI QKD. You have a central node, Charlie. Okay, this is here, it's called center, we call it often Charlie. And so what they do, this is essentially an entanglement swapping scenario. I assume that everybody knows entanglement swapping. Okay, and so inside, so the entangled photon, Bell state measurement in the middle. Okay. Bell state measurement, I'm going to analyze it experimentally in a second. I'm going to explain to you how you do it. So a Bell state measurement, and then Alice and Bob have a click, and by analyzing the outcomes of the Bell state measurement of Charlie in the middle, they can again essentially create a maximally entangled state, and they can extract, they can share a secret key. And so the clever point now of measurement device independent QKD is that you can do a time reversed version of this system, where you say, okay, but actually the measurement of Alice and Bob, the measurement of the one part of the entangled photon pair, and the Bell state measurement of Charlie commute. So actually there is no point, there is no real importance in the order in which you perform these measurements, which means that Alice and Bob can perform their measurements, and then send the outcome, okay, send the photon to the middle, to the center. So it's a time reversed version where Alice has an entangled photon source and Bob has an entangled photon source. They perform the measurement of the one part of the entangled photon pair, and then they send the other part in the middle, Charlie, who performs the Bell state measurement. But then you can show that this is exactly identical from a QKD point of view, from a secret, to Alice and Bob sending single qubit states to Bob, that you don't actually need to perform an entanglement-based measurement here. You don't have to have an entangled photon source. You can just send single qubit states that are like equivalent to having performed the measurement of an entangled photon pair, and you generate the corresponding state locally. And so you can send single qubit states BP84 type, okay, to Charlie, who performs a Bell state measurement, and by analyzing the outcomes of this Bell state measurement, they give them to Alice and Bob. You will see how, and this is how they exchange a secret key. And so what is interesting about this philosophy, this configuration, is that you put all the measurement stuff in this intermediate node that can be completely untrusted. Okay, and this is the major point here, is that you don't have to trust Charlie. You don't have to trust Charlie. So Charlie here in the middle needs to perform the Bell state measurement. He needs to give outcomes to Alice and Bob. And Alice and Bob, out of these outcomes, needs to extract the secret key. The whole point of MDI QKD is that if he doesn't, they will know, okay, because it's kind of reversal of entanglement-based, entanglement swapping-based QKD. They will know when he hasn't, there is no point essentially for Charlie to try to cheat, because it wouldn't lead to the correct correlations between Alice and Bob. Okay, so you essentially introduce with MDI QKD the possibility of having intermediate untrusted nodes. So this brings me to Bell state measurement. Okay, Bell state measurement is a very interesting concept. Okay, and what is it? Okay, Bell state measurement is a projection on the Bell basis. Do you agree on this? Okay, Bell state measurement is a projection on the Bell basis, and it relies. So let me delete some stuff so we can analyze this. And why this is so important? Because Bell state measurement, of course, some of you will know this. It's like a very central building block. Not only, of course, for MDI QKD, but also for everything that is linked to quantum teleportation, entanglement swapping, quantum repeaters, essentially longer, let's say, next generation or long distance quantum networks that rely on quantum repeater all need a Bell state measurement. Okay, so this is an important concept. That's why I wanted to spend just a little bit of time to make sure that you know how to implement it, how you can implement it experimentally, okay? And this is not an easy question. To perform a projection on the Bell basis experimentally is not completely obvious. So to go into the experimental implementation of a Bell state measurement, one has to remember first the beam splitter that we saw at the very beginning, and the property of a beam splitter when two single photons hit it at the same time. Okay, so maybe you know this already. It doesn't matter. I'm going to remind you of this. I guess you do probably, because this is some type of things that we do when we start in the field. Remember here that we had our beam splitter with the two input modes and the two output modes. Going back now to the notation that I was using at the very beginning, okay? The very beginning, not anymore Fock state, forget the Fock state notation. So here you see that if you have a single photon in the zero mode and a single photon in the one mode, so this in my previous notation is going to be looking like this. Okay, don't get scared. It's not anymore the Fock state notation that I was using before. So essentially, this is creation operator on the two modes on the vacuum state, and then using the expressions that we saw before at the very beginning for the operators of these modes, you can easily derive quite easily that this will look like this. 50-50 beam splitter, okay? Which means this is what we call photon bunching, okay? Some of you will of course know this, is when you have single photons that come into a single 50-50 beam splitter like this, the photons bunch. It means that they come out from the same, these look exactly identical. Okay, they come out from a single point. This is the photon bunching effect, and you need to remember that, of course, for this to happen, these two modes here have to be perfectly superposed. Okay, in all degrees of freedom except for the direction of propagation. Okay. Except for the direction of propagation, the spatial mode essentially, they have to be perfectly superposed. And this, we call this, this is quantified or shown very often in quantum optics experiments with a so-called Hongo-Mandel dip, okay, where you see something like that, a dip like that, which normally should go up to the end. Okay, this is the Hongo-Mandel effect. The Hongo-Mandel effect, which essentially means when this is the point where they're perfectly superposed, it should go completely to zero. This is the coincidence count, essentially, in the two output detectors, okay? And you see that the coincidence count should be completely zero when there is a perfect superposition on the beam splitter, between these two single photons. So there is a very similar effect that is happening on the polarizing beam splitter. This is a lot less well known, and I'm going to be using it, needing it for my Bell state measurement with polarization and coded qubits, and that's why I mentioned it here. Remember that we looked at our polarization beam splitter at the very beginning. Remember what we had said is that we have these input ports here, these output ports here. So what is interesting here now is the relationships between this creation and the distraction operators. In this case, here we have, this is the one mode, which can be horizontal or vertical. This is the I'm going to be calling. Oh wait, let's not going to be easy. All right. Let me call this. So the creation operators that are used and distraction operators that are used for this mode is the A1, H, and V. Okay. This one I'll be calling it A2, H and V, A0 I meant. So this is the B1. HB and B2. Okay, and this is a little bit less counterintuitive. So what these creation operators tell us for the polarization beam splitter is that we have A1H equal to B1H. Forever if I'm not clicking, I'm giving you all these elements so that then you can go and confirm the expressions that I'm going to write afterwards. So essentially, this is quantifies, like mathematically formalizes what I had written at the very beginning, that horizontally polarized photons go through and vertically polarized photons get deflected. Okay, this is like a way of writing the same thing. It's exactly what I had said before with these operators, these mode operators, and these are again very important because it allows you to perform calculations. I really recommend it to all of you that want to continue this field to do some calculations of this. Like try to propagate with modes in an optical setup is really a very good exercise. I remember I did it a lot at the very beginning of my PhD. And so this essentially. And then we can use this mode to show that when you have one single photon here that is one single photon here in this spatial mode 1, okay? That for example, I'm just giving you an example that is in the plus state, okay? And in the other, and you have also in the other, you have a minus state. You can show, okay? You can show that you can, and that it will give you a sort of equivalent to a bunching effect by using this state here. Okay, and this is equivalent to a bunching effect. So essentially what this tells you, this expression tells you, is that if you put two single photons in your polarizing beam splitter that have different polarization, okay, so this is your plus and minus here thing, you will get a bunching effect, and you will not get this, and which is interesting, when you do it for the same polarization. If you do this calculation, you will find an expression that I'm not going to write for the sake of time, that is actually shows you there is a probability of having the photons in here, or split in the two output modes, okay? So, and this is interesting because this is exactly what will lead us now to the polarization and to the polarization beam Bell state measurement, which will look like this. Okay, I'm going to write it a little bit in a way that is going to be a little bit weird, but it's going to allow us. So we have first the beam splitter. We have the input, the 0 here and the 0, 1. Okay, here we have the output of the beam splitter with the modes A3 and A2, okay, exactly like we saw before. And then each one of them go into a PBS. Where we have the detector that does one V. Okay, and this is a Bell state measurement. This is an experimental Bell state measurement that works. And this is important what I'm going to say with linear optics, okay, with passive linear optics. This is important. And what can it do? This is the question. What can you do? What would you like a Bell state measurement to do? What did we say before? You would like it to project, to be a projective measurement on the Bell basis. Okay? I remind you here, everyone, what is the Bell basis? Let me write it here because you will be able to see the Bell states. Basis. All right. Okay, so we want this one, the Bell state measurement that you see here, to be a projective measurement of these states. What does this mean? Is that you want to see what happens when each one of these states enter this device, right? You want to see what it creates, because what you will have, any two-photon state can be written at a Bell basis, a superposition of this. They form a basis, right, of these Bell states. And so by doing this, you essentially perform this projective measurement on the Bell basis, and you can in the outcome, the P of M, essentially the outcome of your device will be which Bell state you have actually projected onto your state. And so what is interesting now to see is that if you enter this state here, okay, this is a special state. It's called the singlet state. It's one of the 4 Bell states that is particularly interesting. It's the singlet state, while all the others are called triplet states. Okay? So the singlet state is a kind of special importance in quantum information. It's interesting to see that it's the only one that is anti-symmetric, okay, upon when you change shift, okay, when you change the position of your qubits, okay. And so this is actually quite important. This is the fact that it has this asymmetric wave function in the polarization makes it, that's why it's called singlet, and it actually makes it easier to detect in this device. What you can show by combining everything that we just saw before, by combining the fact that this is, what happens with the plus plus, minus minus, the plus minus and the minus plus states that we saw before, and the equivalent when they have the same polarization. If you put the input, now that you have all the equations with the operators, you can enter this psi plus state and psi minus state in here and see what happens, with this creation and destruction operators that we have seen. I really, really recommend doing it. It will be satisfactory just to do this calculation, okay? To put it as an input in there and see what happens when you go through with following the modes, with a different device, with the different mode operators that we saw before, how they react to the beam splitter, to the polarizing beam splitter, and you will end up with a state that will show to you what will click, okay, essentially. So essentially what you can show is that the psi minus state will create coincidences. So I'm not going to write it, but essentially this is a state that can be written like, if you want, like this. You have to create the H state, okay. At the same time, the polarization and the spatial modes, okay, on the vacuum, and then you do your calculation, okay, that I'm not going to do, and what you find is that you find this expression that looks like that. Which essentially means is that you will get coincidences, okay. Either on the detectors, if you follow the paths, okay, either on the of these detectors here, it will be either on the D18 and D2V, or the D28 and D1V. So you will get coincidences between this detector and this detector, okay, if you enter a psi minus state, or between this detector here and this detector here, okay, which is quite interesting, which essentially means that for the psi minus state, you didn't even actually use this, you didn't even need this part of the setup. You could have just done a single photon detector here and a single photon detector here, and you would still have coincidences between these two for the psi minus state. So actually the Bell state measurement that projects onto the psi minus state in polarization, it's just a beam splitter. Quite interesting. It's a very, very simple device. But by adding these polarization beam splitters, you allow this system to also project onto the psi plus state, okay? And so that I'm really not going to write, but the psi plus state, if you do exactly the same calculation, it will give you that you will get coincidences either between these two detectors or between these two detectors. Okay, so in the same part of the setup, which is kind of makes sense if you think about it, okay, because they go, let's say, in the same direction. So you go in this part of the setup or in this part of the setup, you will get coincidences between these detectors or these two detectors. And so, and phi plus and phi minus with this beam split Ball state measurement, sorry, based on these linear optical elements, you cannot discriminate. Okay, so this is a Bell state measurement that has an efficiency of 50%. 50% in the sense that you can only project in the psi plus and the psi minus state, but you cannot do this for the phi plus or the phi minus state. And again, we know that a full Bell state analysis is possible by introducing non-linear elements. For example, if you introduce a C-node gate, a control NOT gate, which can only happen with a non-linear optical elements in optics, okay? You can have a full Bell state analysis, but because of the importance of Bell state analysis and Bell state measurements in quantum information in general, this is a very, very, very high research topic of high importance on how to optimally, how to improve this 50% efficiency, the projection efficiency of Bell state measurements with linear optics, if possible, to avoid gates. And there is quite a few works now that have like included ancilla qubits and some photons, extra photons in the thing. So there is quite a bit of theoretical and experimental work on how to improve the efficiency of Bell state measurements. So this is why I'm like putting a lot of emphasis on this, because it's an interesting topic and kind of important for quantum information more globally. And so essentially this concludes this is what I want to say on this polarization Bell state measurement. And so then, if you want to do the MDI scheme, the measurement device independent scheme based on this, you can. It will look like this. It's exactly what I have just plotted. So you see that you have the single qubit generated by Alice and by Bob. Okay, they are sent into Charlie, and so this is. They are measured by Charlie, who, as we said, can be an untrusted party, and then Charlie communicates the information on the BSM output to Alice and Bob, and so Alice and Bob, just to give you the final touch of the protocol, if they wanted to have an identical bit string, they need to do some bit flip depending on which state has been identified. For example, you see here that if this state and on which basis, right? You need to be able to write these states also in the X, but also in the X and the Z basis. And so in this case, you will see that in the while psi plus has different polarization in both the X and Z basis. Psi minus in the Z basis has different polarizations, but if you write it in the X basis, it has the same one, and in that case, Bob does not need to do a bit flip. Okay. So this is a little bit of a detail. This is a little bit of the post-processing of the MDI scheme to be able to actually for Alice and Bob to recover identical bit strings by using this MDI scheme. So I'm not going to talk about it at all, but there is a very important variant of the MDI scheme that is called twin field, okay? QKD, some of you must have heard it, okay? Twin field QKD is kind of a little bit the same concept, except that it's based on single photon interference, while here, as you see, we're putting like two photons in the Bell state measurement of Charlie. In twin field QKD, the encoding is done in phase, and you only put one photon, and so so it's single photon interference. It's very loss efficient, so it can allow to beat the so-called repeaterless bound of QKD. Okay, that deserves another hour of discussion. So I'm not going to go through this, okay? The whole discussion around like this rate in the QKD, and it has been used, this type of single photon interference protocols, this twin field. It's for the experimentalist among you, it's a little bit quite hard, because you essentially need to have a joint phase reference between Alice and Bob in twin field QKD, which is hard to do at a long distance. For those of you who know this, it's very hard to do for remote Alice and Bob over hundreds of kilometers to maintain a phase reference. But there has been a new variant more recently, which is called mode pairing QKD. Okay, it never ends, which is again a variant of twin field that appears to solve this problem and makes it easier to do this. So stay tuned. So essentially, this means that it never ends, right? There is new QKD protocols that appear. So we have focused a lot on BB84 and decoy, etc. And I've told you there is a reason why. But it's actually, there is many protocols. I know, Ramona, I have finished my, can I use 5 more minutes?
Sure.
Okay, okay, 3, 5, okay. Just to say a few more words before we finish. That was essentially, I don't have any more written a couple of slides. I did not want to leave you without saying a few words about continuous variable QKD. I know it's going to be not a lot, and from an experimental point of view, so I mean, there is a whole world of the security analysis of continuous variables protocols, okay, or curious protocols, but I just wanted you to not leave the school without having seen just a little bit of the encoding in continuous variables. So this is something that physicists are very comfortable with. I've noticed that mathematicians and computer scientists are very uncomfortable with continuous variable encoding. It's a kind of, they really cannot get it. It's a kind of, encoding in infinite dimensional space. So while in discrete encoding we use qubits, okay? We use qubits, of course, as you've seen, and so discrete variables. In continuous wave we use typically, so this is a little bit of an old slide, but anyway, we use the continuous values of the quadratures of the electromagnetic field. So it's interesting from a practical point of view. It's not anymore that we use, for example, coherent states to simulate single photons, and we spent quite a bit of time to see how you do this in discrete variable QKD. In continuous variable QKD, you naturally encode information on coherent states, okay, or on squeeze states, so or whatever states that are performed, where you can have these continuous values. And so, from a theoretical point of view, it changes the description. Here we've worked with density matrices. In continuous variables, we reason with Wigner functions, okay? And symplectic, so this is maybe some words that some of you will recognize, symplectic eigenvalues and this type of things. Measurement is extremely important. We have focused a lot during this discussion on single photon detectors. In continuous variable, we use the so-called coherent detection techniques that rely, here you see an example of a homodyne detection, where you put a phase reference. This is called local oscillator in continuous variable QKD. You mix it with your continuous quantum state on a beam splitter that you know, a 50-50 beam splitter. The output, you get 2 standard classical photodiodes. And you can show that by subtracting the electrical output, the signal of the 2 photodiodes, you can essentially detect the quadrature of the electromagnetic field here, because it has somehow amplified by the local oscillator, which is a classical signal. Okay? Although it's very slow, very low, very small amplitude, you can actually detect your quadrature by doing this clever technique. Homodyne detection, they have very huge, very high efficiencies, and they do not want a cryogenic temperature. So there is a disadvantage of room temperature operation. So simple state, we have seen Fock states for photons. Gaussian states are the ones that are typically used for QKD and continuous variables like coherent states or squeeze states. But if you want to do, just as a side note, CV quantum computing, with quantum, you also need non-Gaussian operations. Okay, you cannot use full Gaussian quantum information and perform full quantum computing. But for QKD, it's perfectly possible. Post-processing, while in discrete in DVQKD is quite easy, there's quite complex post-processing in CVQKD, exactly because of the same reason. You basically measure noise, okay, all the time, noise variances, and out of all this noise, you need to extract somehow your bits, information, useful information. So this is more complicated. QKD, and in terms of security, we've now gone through everything. I think in discrete variable QKD, maybe I don't know if finite size were discussed at all during this school. Yeah, okay. So finite size effects were discussed. Okay, so this is important from a practical point of view as well, not from an experimental point of view. It's very important to consider that you have finite amounts of data for your parameter estimation. And so in CVQKD, security tools are also quite advanced. There is a few little things to do still here. Maybe I won't have the time to go through all the details. This is an example of how a coherent state CVQKD system will look like, okay? So there is a constellation of coherent states that are characterized by this fundamental short noise, and you move into the phase space, you create your coherent states. This is what are sent. Actually, it's not weak coherent states in the sense that we saw for decoy state QKD, but they are weak in the sense that we don't have any more, we don't really reason with this average photon number per pulse anymore in CVQKD. What we reason about is this amplitude of the variance of the constellation. So basically, you pick your states, your coherent states in the phase space, following a certificate distribution, and this kind of corresponds to a few photons per symbol. Okay, this is more or less what it comes down to. It's not anymore single photon state or whatever, but they are not like classical signals that you would use in classical optical communications. They are a few photons because you want your coherent states to be grouped together, because in the uncertainty that is created by the short noise, the fundamental noise, this is where the security relies as well, right? Because they become non-orthogonal when they are close to each other, and so you can use the uncertainty principle. The Eve cannot discriminate them, and the whole security relies on that, right? And then, but there is all sorts of different variations of the protocols where you can use Gaussian distributions or you can use so-called discrete modulations. And then you go through the quantum channel, transmission efficiency. Now we have a new parameter that we use a lot in CVQKD, which is excess noise, which is any noise that is beyond the fundamental noise that is associated with coherent state. It's a really critical parameter in QKD. And then you mix it, as we said, with a phase reference. And you have the coherent detector, which is close the characteristics that we saw in single photon detectors. You have the quantum efficiency and the electronic noise, which is very important here. You don't have any more the dark count noise. You have what is called electronic noise, which is a bit what happens in the coherent detector when you don't have any signal. And so, from a security point of view, we have composable finite size security proofs for Gaussian modulation. So all the tick boxes are clicked. So unfortunately, we don't have the time here to discuss all of this. And there is a lot of work currently to be able to show the security, full security in finite size regime. It has happened already for asymptotic limit for discrete constellations, and the final step that is underway is doing this. And from an experimental point of view, what is interesting here is that you also need quite difficult processing, digital signal processing techniques, especially because of this, because you need to somehow, the post-processing, as we said, is more complicated, so you have to have good correlations between what Alice has said and Bob has received, despite all the noise. So you need to be able to correlate these events here with these events here, which means that you have very important techniques that are used for, we call this digital signal processing in experimental work, to be able to improve, to reduce the excess noise and optimize this correlation. Yes, maybe I won't have the time to go through this. I just wanted to show you a little bit. A few years ago, we had written with some colleagues this, trying to put everything, all this information in a single graph is very hard. I think there is a couple of more recent review papers. The one that I mentioned here, for example, this one is a good reference. is a good reference if you wanted to check. It's from 2010. It's a nice comprehensive review paper that gives lots of interesting and references from 4 years ago on what you can do on QKD. So I recommend it. It's a nice, and maybe there is even a more recent one. Sure. But and there is a little bit more updated things on MDI, twin field, etc. that you can check. So. So yeah, and with this I think I'm going to conclude. Thank you very much.